Good evening and welcome to this final lecture in the Institute of Physics, Hereford of Worcester 2023-2024 lecture programme. And it is my absolute delight and honour to welcome Dr. Greg Adamiec to talk this evening about the important international field of authenticating ceramics. So unlike other methods of authentication, thermoluminescence is a scientific and quantitative method to date pottery and verify the origins. So we're delighted. Greg is actually joining us from Poland. He has over 30 years of experience of thermoluminescence. He collaborated with the founder of Oxford Authentication, Doreen Stoneham, since 1993, when they were working in the Oxford Laboratory for Art and Archaeology, developing techniques. Doreen set up Oxford Authentication in 1997, and Greg was involved as a consultant, and he became the chief scientist about 5 years ago. So we're absolutely thrilled that you're here to join us. I'm going to stop my video and allow you to take over, Greg.
Welcome. Good evening, everyone who joined us. Thank you, Nikki, for that introduction. Let me just share my presentation with you for today. Oh, sorry. Oh.
Sorry, can I just quickly say, I'm so sorry, while you're sharing your screen, carry on.
Yes,
if anybody has any questions, please put them. You've got two little speech bubbles at the bottom of your screen. Please pop those questions into that Q&A. You won't be able to speak while we're doing this, but hopefully that way it means we can get through as many questions as possible. And obviously, we're going to try and save time at the end in order to use that. We will be stopping the video and muting everybody so that we can maximize the bandwidth. And then at the end, with a quick apologies, when the Zoom meeting finishes, it will be finished, and that is quite abrupt. But that's just, I'm afraid, the way that Zoom works. So I'm sorry, Greg. Do carry on. Thank you.
No, thank you. Is it genuine? The question that we ask ourselves when we see objects of art. Before I get into the details about thermoluminescence, I would like to answer the question: what is a forgery? And a definition could read like that: forgery refers to a historical document in general, or a work of visual art in particular, which was created for the purpose of malicious deception. And forgery is only proven when malicious deception is demonstrated. Proof can be provided through stylistic critique, iconographic, and technical findings. So that's for the definition. In authenticity testing, we aim at establishing the authenticity of an object. On the right, you can see a figure of a squatting drummer, one that were often placed in graves in China in Eastern Han during the Eastern Han Dynasty, and they were providing entertainment in the afterlife to the deceased. What are the methods of authenticity testing? Well, we have material and technology analysis, and because materials and technologies change over time, we have this kind of time marker philosophy. So knowing that an object was created using a certain materials or using a certain technology, we know that it cannot be younger than, but this kind of dating is not very precise. We can do stylistical analysis and dating, which is based on physical methods. The complications in authenticity testing are that forgers can be very clever. Details of ancient techniques and technologies have been studied very widely by scientists and are published in scientific literature. We have to outwit those forgers and be better than their methods, which is not always easy. In dating in authenticity testing allows us to establish the true age of the object, but maybe there's a slight difference from typical dating applications, because here more often we try to determine whether the age of the object is consistent with its expected age, because we are often limited in the amount of material that can be taken from a sample. The accuracy is not as high as in normal dating. Before we go into details, what is thermoluminescence? Namely, when certain minerals are heated, usually to a few hundred degrees centigrade, following the exposure to radiation, they emit very weak light. And, the first account was given by Robert Boyle before the Royal Society in 1663. At night, he observed a very faint glow of diamond held upon a warm part of his body. That's a citation that's given by Martin Aitken, one of the main scientists who first developed TL dating. On the right-hand side, we see a photo of thermoluminescence emitted by calcite, which is a mineral known to emit quite a lot of thermoluminescence. Here we see quite unusual photographs of thermoluminescence emitted by a quartz crystal. These photographs were published in 2007 by a Japanese group. And in this case, you can see that there is a thermoluminescence emitted while heating from minus 196 degrees to 0. And then on the image next to it from 80 to 400 degrees centigrade. I will tell a little bit more about the mechanism, how luminescence is, about the source of thermoluminescence a bit later. In general, there are actually many dating methods based on physical measurements. One, probably the most widely known one, is radiocarbon dating, which is based on the decay of the C14 isotope of carbon. It has the limitation that it can be applied almost only to objects containing organic materials. Roughly speaking, this method dates the time of life of the organism from which the materials originate. But in materials like ceramics, usually there is no organic residue, no organic contribution. So this method is not very useful. What is required for dating? There are a few conditions that have to be fulfilled in order for dating to be possible. And first of all, we need a unique event critical to the formation of the object that sets the clock to 0. And in the case of pottery, this is firing in the kiln. This is the time when the clock starts ticking. You could also say is the last heating of an object to a high temperature. Then the next conditions, we need a continuous process which is practically unaffected by external factors such as heat and light. And in the case of thermoluminescence dating, this is absorption of radiation originating from radioactive decay in the clay itself, plus a small contribution from the environment. I will talk about a little more in detail about all this a bit later. The object must contain substances that accumulate the effect of that time-dependent process. In the case of ceramics, these are TL minerals, mostly quartz and feldspars. And finally, we need a method of measuring the time-dependent process. And since thermoluminescence is radiation-dependent, heating the clay, that is the TL minerals, gives a signal which can be related to the total absorbed radiation by the piece, the total absorbed radiation since the zeroing effect. Okay, so This can be illustrated by this very simple graph where we have the latent luminescence, and the initial part here shows luminescence acquired before the zeroing event, because radiation is present in the environment all the time. And then during manufacture, we zero the TL signal. And then when the object is stored, is being used, luminescence slowly, this thermoluminescence slowly is increased up to a point when we take the sample to the laboratory and we measure the level of thermoluminescence. So that's this very simple way of presenting the process of TL dating. And you actually, there is a question which could be asked: what is the link between a Ming vase, the body of a murdered girl, and the site of the world's worst nuclear accident? And it's this very same technique, the thermoluminescence technique, can be used to date ancient objects, or maybe not so ancient objects, like in that one case where a brick retrieved from the crime scene was dated, and it allowed to find the perpetrator. And the radiation dose in places of nuclear disasters can also be determined using this technique. So it's very versatile, and even today, new applications are being published. What's the history of using TL? TL thermoluminescence is very weak most of the time, except with the exception of some minerals. It's really very, very weak. So we need special light detectors, and it's in the 1940s that photomultipliers were developed, and these are very sensitive light detectors, and which can record single photons. And we can count those single photons. So they are extremely, really extremely sensitive. In the 1950s, TL was used to measure exposure to nuclear radiation. And for the first time, TL from ancient pottery was detected in 1960 in Bern and California. In the 1960s, the TL was developed for archaeological dating at Oxford, Kyoto, Wisconsin, Philadelphia, and Denmark. And since the 60s, this technique has been developed and refined. With time, more and more detailed studies allowed to perfect the technique. A few words about how thermoluminescence, how this process occurs, and this is the band model of a solid, where we have the valence band, the conduction band, and when we are dealing with minerals like quartz, they are insulators. There are no free electrons in the conduction band. So what happens when ionizing radiation hits such a crystal? Pairs of holes and electrons are created. Electrons find themselves in the conduction band, and they can travel. And what can happen to such an electron? It can recombine, emitting light, but it can sometimes get captured at sites which are so-called traps. These traps are associated with defects in the crystal lattice. And some of these traps, or maybe electrons trapped in those places, can stay there for a very long time in the environment. So when the temperature is low, around 10 degrees, 20 degrees centigrade, these electrons can stay here for hundreds of thousands or millions of years. So during this irradiation, this exposure to external radiation, more and more electrons get accumulated at those trapping sites. And this situation is shown on the middle diagram. These electrons accumulate, there are more of them, until we get a sample to the laboratory. And when we heat it, the electrons get excited from those trapping sites into the conduction band, and they recombine, emitting light. And this light is our thermoluminescence, is the thermoluminescence that we are measuring. So the more electrons are captured in those trapping sites during heating, the more light will be emitted during heating. And this is the simplest way of visualizing how this thermoluminescence production occurs. Since 1988, another method, OSL, optically stimulated luminescence, has been dynamically developed. And if we went back to the previous graph, here instead of heating, it's illumination with blue or green light that excites the electrons into the conduction band. And this method, OSL, is extremely useful in dating geological sediments. So really the number of papers that have been published is increasing every year. More and more applications are shown in geology, geography, in general, in investigating the Earth environment. So what are the types of ionizing radiation? Because this is what causes the ionization of, the production of electron hole pairs. And here for dating, we have alpha radiation, which are helium nuclei. The range is about 20 micrometers in solids. And they originate from within the clay, from within the object. Beta radiation, these are electrons, could be also positons. Their range is about 2 millimeters in solids. They also originate from the clay. And then we have gamma radiation, which are high energy photons. Their range in solid state are of the order of tens of centimeters, and this radiation originates from the environment. And then we have cosmic radiation, which originates from space, and it's usually a small contribution to the total amount of radiation absorbed by those ancient objects. This could be a more sizable, relatively larger contribution if we had environment with very low natural radioactivity, but that's very rare. And in archaeology, in authentication, usually does not happen. So, what are the sources of radiation in our environment? And here in the Earth's crust, everywhere there's uranium-238 decay chain, uranium-235 decay chain, thorium-232 decay chain, as well as potassium-40 and rubidium-87. So these are 5 elements in our environment that are present everywhere, unfortunately in varying concentrations. So if we want to perform dating, we have to determine the amount of those radionuclides, those radionuclides every time. And on this diagram on the left, we see the example of uranium-238 series, where we have emissions of alpha particles going across on the diagonal. So we have one alpha particle, then we have a couple of beta particles. And subsequently, we have several alpha particles being emitted, then again beta particles. In nature, this chain is in so-called secular equilibrium, meaning that the activity of each of the elements of this decay chain are the same. Apart from those alpha and beta particles, also gamma rays are being emitted. Potassium 40 emits beta and gamma radiation, and rubidium 87 emits beta radiation. So in order to determine the amount of radioactive elements, we need to know all those the contribution from all those elements. How do we go on about dating a pottery object? First, we need to take a sample. So the drilling site should not be obtrusive. It cannot be very visible. The drilling has to occur in dim amber or red light so that this light does not affect the result of our measurements. And of course, we have to clean the sample, so remove any kind of soil or any kind of contaminant that might be on the outer layer of that object. Here we see on the photo a sample being taken, and this is done by means of a small handheld drill, which is fitted with a triangular tungsten drill, the same one that's used in dentistry. And we have the powder is collected on weighing paper, as shown on this photo. And in order to do an authenticity test, we need to collect about 100 milligrams of that sample. That's enough to perform this dating. After drilling, the sample is stored in a vial and sent to the laboratory. Then we need to extract from that powder the right grains of the right size. Usually we select 4 to 11 micrometers, and this is done by sedimentation from acetone. So by letting a suspension to settle for a given amount of time, we can target these 4 to 11 microns grains. Next, these grains are deposited on aluminum discs. They have about 10 millimeters diameter. And we let the suspension evaporate in an oven at about 50 degrees centigrade overnight. And the grains deposited on the disc, that's quite robust. These grains don't fall off very easily most of the time. So these grains are then ready to be measured, and that's done by a device, nowadays an automated luminescence reader, where a number of such discs can be placed. And this reader is fitted with an beta source and alpha source. I will also say a few words a bit later on that. And such a reader can be programmed to perform a sequence of measurements needed to estimate the amount of radiation absorbed by the grains. So here we have an example of two objects. These are Hasila twin-headed vessels. So that's from southwestern Turkey, the oldest objects dating to 7040 BC. And what are the results for these objects? On the left, we have a genuine one. On the right, a fake one. What would the thermoluminescence look like? And here we have examples of glow curves, so-called glow curves. And this is the amount of light emitted during the heating of those grains up to 500 degrees centigrade. This graph shows thermoluminescence curves for a genuine sample, where here with letter A, labeled by letter A, we have the glow curve recorded for grains extracted from the vessel as they are, and curve B shows the TL glow curve recorded after irradiating those grains with a non-laboratory dose. And this is exactly for that reason we need automated readers that can irradiate our samples with given doses and heat them to given temperature, because every sample is different. So the sensitivity, the amount of luminescence emitted per unit radiation dose is different. So you could say that every sample in a way needs to be calibrated with the laboratory beta dose. And here also curve C is shown. This is the black body radiation. This is light emitted by any object that is heated to high temperatures, and that needs to be subtracted. This is our background. So in this case, we see that the natural sample, the grains as they were taken, they have quite a lot of TL compared to the ones irradiated with the laboratory dose, and the calculations yielded a genuine result. On the other hand, for a fake object, curve A, the one recorded for the grains as they are, there's no signal. The sample is sensitive to radiation. After irradiating the grains in the laboratory, there is signal, but there is no signal in the natural sample. And that's, in this case, it's clearly a fake, a modern forgery. So how do we calculate the TLH? So first of all, we need to measure the TL signal that will allow us to get the total absorbed radiation by the clay. And then we need to measure the internal radioactivity because this will give us how much radiation the grains were absorbing during burial since manufacture. Then we combine the two to give us the approximate date since the piece was kiln fired. So that's given by this very simple H equation, total absorbed dose over the lifetime divided by the annual dose rate. Unfortunately, there is a technique called alpha counting, which allows us to obtain the radioactivity even for such a small amount of sample, like 100 milligrams. Also for potassium content, which needs to be determined, it's enough. For this, we can use various chemical methods, or we can use the X-ray fluorescence. So the environmental gamma radiation, that's a bit more tricky element, because when we have an object taken from, let's say, from a museum or from a collection, we don't know in what conditions, at what locations these objects were stored. So we cannot be sure what kind of gamma radiation was absorbed by those grains, and this has to be estimated. The amount on Earth varies quite a bit, but fortunately, usually the uranium, the contribution from uranium, thorium, and potassium are much larger than the external dose rate. So it's not so crucial. And in authenticity testing, often it is enough to give us to be able to say a given object is consistent with the attributed time or not. What else can we date? We can date also bronzes, but not, of course, through dating metals, because thermoluminescence is emitted only by minerals, by insulators. So bronze as metal is not suitable, but during the production of bronze objects, casting cores were used, and often there are remains of those casting cores inside the bronzes. So when we are able to get hold of a sample that was fairly close to the surface of this bronze object, we can also date those. And here is an example of a bronze rhino. It's an interesting one because it's got scales, and rhinos in China died out about 1,000 years earlier, before the Tang dynasty. A verbal description existed, and in the Tang dynasty, some of those bronzes appeared. The descriptions became garbled, so this is like a cross between elephant crocodile skin, but this particular piece was proven to be genuine. So maybe by visual inspection it might look a bit odd, but TL gave an authentic result, a genuine result. Now, a question that should be asked. So far it looks very good. It seems like we've got an answer, but can TL always give the final answer? And here we have two objects. These are those two examples of squatting drummers. And the question is, are they genuine? And I can tell you that on the left-hand side, the squatting drummer is authentic. Well, what about the one on the right? It looks pretty old, but after X-ray inspection, turns out that it's been assembled from a large number of small, much smaller pieces. And further, after removing the outer layer, we can even see with the naked eye that it's been put together from pieces, and this is most likely a forgery where some useless fragments of old pottery were glued together using plaster or another material, then covered with some slip. In TL, measurements appear to be genuine, but actually this is a modern forgery just assembled from old fragments. So sometimes for authenticity we need a four-pronged approach. So TL age of clay is only one of those elements, but sometimes CT scans or X-rays can show us breaks or insertions. The piece may still be 100% genuine, just because it's got some elements added doesn't automatically mean it's all a forgery. Sometimes Fourier transform infrared spectroscopy can be used to show the presence of organic material, like an adhesive that was used to put an object together. And then also some spectral analysis of the slip may also be useful. So how a process of forgery or building of a forgery might look like. So here we have some not really nicely looking two parts and some smaller fragments, and then they are all put together, assembled, covered with slip, and we have a much more interesting looking gold Triton. So this is something that's this could be a real forgery, but this has to be distinguished from another case like shown here. Here we have a number of fragments. Each of those fragments is genuinely ancient, and these are actually parts of a genuinely ancient object that after putting together is a deer Triton, and it's assembled from old fragments, but originally it was this object. So sometimes it can be very tricky to determine whether a given object is a forgery or just a reconstruction. Here we have another example of a tank hose, a very beautiful tank hose, which is genuine. And another one which is totally fake. But what is interesting here is that the forgers, knowing which parts are most likely to get sampled, so this could be the base or maybe the underbelly, there were some old fragments inserted into those parts. And here it's shown a number of samples taken from the base and from the belly, which were ancient, but they were not representative for the whole object. So these are traps that lurk in such objects. Another result, another example of an object assembled from pieces covered with slip. Another hand hose, which is also consists of a number of fragments. So in general, if forgers can get hold of some old, genuinely ancient fragments, they can assemble a genuinely looking object. So what can we use? Yes?
There's a question.
Yes.
Is there a problem if objects have been heated during their lifetime by events such as volcanic eruptions or like Pompeii or Vesuvius? Does that disrupt anything?
Yeah, I mean, any kind of heating above, I don't know, I would say 300, 350 degrees during the lifetime will reset the signal again. So yes, we are assuming that the object was not heated to a high temperature during that time.
Thank you.
Yeah. Okay. So so what can TL help us with? So sometimes we see presence of organic material. This is a so-called spurious signal, and that's basically a signal that's not behaving like a typical signal that would be observed from quartz or feldspars. So that might indicate presence of organic material, like a kind of adhesive or some admixture of, I don't know, sometimes maybe materials used to not conserve, that's the wrong word, but to preserve an object. Sometimes if we take a few samples from one object and the shape of the glow curves differs a lot, this may indicate that these different parts of that object were manufactured from different types of clay, which might ring our alarm bells. Partial heating, exactly when the object was heated to a high temperature, I mean that's certainly a cause of problems. Yes, and restoration material. If the TL glow curve has an unusual shape. So I would like to say a few words. I have a few more minutes, so I'll try not to talk for too long. Porcelain. So far I talked about pottery most of the time, ceramic. Porcelain is a little bit different. It's also a type of, it is ceramic, but it's during manufacture, it's vitrified. It's heated to much higher temperatures, between 1200 and 1400 degrees centigrade. So a high proportion of that of porcelain is vitrified, and actually it's useless for TL analysis because either it doesn't show TL or the TL is not very characteristic. And in the case of porcelain, we take the samples in a bit different way. First of all, we use a coring drill to take cores. We don't sample powder, but a diamond core drill is used. And the cores are about 3 millimeters in diameter, about 4 to 5 millimeters long. And they are always taken in an unglazed part of the object, almost always in the base. Obviously, sorry, the sampler has to be very careful not to damage the object. Yes, and no, we don't go we don't go through. So here we have a photo of this process of taking a core. Again, it's a handheld drill with a diamond coring drill drill bit, and here we see this a core that was taken from porcelain. Subsequently, in the lab, we have to slice it, and for that we use again a diamond a saw with a diamond-coated blade. It's the slices are about 200 microns thick. The saw blades are also very thin, so that we don't use a lot of material. We obtain a few. We can obtain a few slices from a core like that. And here I just wanted to show you on the left, it's an SEM image of a cross section of a porcelain slice. In this particular case, it was modern porcelain. And here we can see that there is one quartz grain still undissolved in the matrix, but otherwise most of the grains are dissolved. And on the right-hand side, we see an image of thermoluminescence emitted by a slice. And here we can see that most of the TL is emitted from possibly one grain, and maybe a little bit more from a few other sites. But this is not, I mean, there is not a lot of there are not many grains in such a slice. So here we say that basically quartz grains smaller than 12 microns, they dissolve in the feldspatic body and they become glassy. They have no there is no TL emitted by this fraction. But the remaining crystalline quartz can emit TL signal. But for this high temperature signal that I showed you before, emitted above 300 degrees, the sensitivity is too small. There is not enough TL to be useful for dating. And for that reason, we use a different approach. We measure the change of sensitivity of a 110 degrees peak. So this is I think on an example it will be easier. So this is a TL glow curve of a porcelain, and we see that there is a TL peak at 110 degrees. This peak is not present in natural samples because it's not thermally stable. It has a lifetime of a couple of hours at room temperature. So this peak is induced in the laboratory. And in this case, the interesting thing is that its sensitivity depends on the amount of radiation absorbed before. And without going into the technical details, here we see an example of an object that was found to be genuine, a fish bowl, and another one that looks actually much older, but unfortunately, turned out to be a forgery, a fake, a modern bowl, and there are many objects being produced at the moment that are purporting to be old, but they are just modern forgeries. So we can prove that by means of thermoluminescence. What are the limits of TL? I mean, there is the accuracy of dating of a so to speak, full TL dating. There's about 8-9 degrees, but sorry, 8-9%, but that's only in the case when we know what is the environmental radiation, the moisture of the environment, which also has influence on the amount of radiation reaching an object. For authenticity, it's usually about 20%. This is an error limit that's safe to quote, and it contains random measurement error and a systematic error, for example, of calibration. For porcelain, we do not have faith in composition analysis. Scientists have published the composition recipes of all glazes, and forgers ardently follow these recipes. So there are factories which can mimic these old technologies, and just using composition or technical analysis is not good enough. It won't help us determine the authenticity of those objects. In the case of porcelain, we have to be very aware of inserted bases, and maybe I'll just show you an example of a vase where we see the base of an object, and only under closer inspection we can see here that this base was attached to the body of that object. So of course, if we take a sample from the base and we don't inspect the object very closely, it may turn out to be I mean, we could be fooled because this base is ancient. That's what the forgers do, and the rest may be just a modern object manufactured in a factory. And here we have another example of a porcelain pot that was irradiated artificially, possibly with a cobalt-60 radiotherapy source. And then the forgers also try to mimic the irradiation during burial by using such radiotherapy sources. So there are many traps waiting on our way to determining the authenticity of an object. And just to a short summary, that TL is a useful technique that can be applied to all ceramics of all ages and cultures. But for maximum effectiveness, it is best to take several samples, sometimes do CT scans to show insertions and joints, maybe use this FTIR to check organic materials in the clay, and maybe examine the pigment separately to complement this method. So TL dating. So that's all that I wanted to tell you tonight. Are there any questions? Thank you.
That's brilliant. So yes, we've got a question waiting here, but please pop the questions. Please type the questions into the two speech bubbles that are at the bottom, the Q&A, and Greg will be delighted to answer them. So we've got a question about forgers. So could a forger irradiate an object using a prepared radiation source or a reactor to simulate age?
Yes, they could, and that's happening. But of course, well, in they have to give the right amount of radiation, and that's of course a bit of more problematic because the source has to be calibrated to give the correct amount of dose for the given object.
Is it just the dose, the total dose that matters? Or is there a difference in the fact that a genuine object has been sitting in its environment over a period of time and has acquired that dose in small stages? Or are we just interested in the end amount, the total amount, or how
yes, I mean, in general, this external radiation is much more uniform. Natural radioactivity of the clay is quite varied between grains. So, in theory, there is less scatter in the luminescence recorded from artificially irradiated objects, and also theoretically you could imagine a method where you use different sizes of grains to date different fractions, and they would differ then depending whether there was just external gamma radiation or this internal alpha, beta, and gamma radiation. Yeah. So, but it's tricky. It's not straightforward due to accuracy restrictions and.
And there was another quick question you mentioned right at the start about Boyle, who could see emitted light from diamonds just by placing this on him. Is that just a story, or is that
no? Apparently, that's what Robert. Apparently, that's in the Proceedings of the Royal Society from October 1663. And that's what Robert Boyle, reported. And yes, because diamonds are insulators, and possibly, this whatever 35 degrees could be enough to induce, to release some of the thermoluminescence. And after a longer time in darkness, our eyes get adapted. So, I don't know what's the wavelength of thermoluminescence emitted by diamonds, but I mean, it could be possible that after your eye gets adapted and the TL is in the right wavelength, that our eyes are quite sensitive. Yeah, I think that's
fascinating thought of all of us clutching our diamonds under the bed.
Yes, yes. This
Martin
sorry,
book, isn't it?
Yeah, I don't know why.
Yeah, it's only thermoluminescence dating.
Yes, that he gives this this report in his book, so I'm repeating it after Martin.
There's a couple more questions. You mentioned FTIR. I'm not sure what that stands for, but what sort of sample is required for FTIR?
So FTIR is the Fourier transform infrared spectroscopy, and it's a sample in powder form, and basically by investigating the spectrum you can tell what kind of molecules are present in the sample, what kind of bonds. So in theory you can detect certain chemical compounds.
Okay, thank you.
Mm-hmm.
How does the technique compare with rehydroxylation in terms of applicability? Sorry,
Okay, so I have heard that term. But to be honest, I don't know details of this technique, so I can't answer that question.
Fair enough. And is there a way to mark an object as fake or genuine so it doesn't need to be tested again in a few years, for example?
Well, because we take our samples, either we core or we drill the samples, we leave small marks. So often for collectors or museums, they know that the object was tested, so they could request the owner to provide that test. But yeah, I haven't come across any kind of fail-safe method of marking them, because of course if we make a forgery looking exactly the same, yeah, just a photo, of course, all the tests are, all the objects are photographically documented, etc. But yeah,
I do
so
remember I was at the Three Counties Showground, which people here may be familiar with, and there was actually an object there with the certificate from Oxford Authentication, and the seller was very keen to show the holes drilled in the base.
yes.
But I suppose as well, if you find a way to make the mark on the object, then I imagine the forgers will be very quick to
Yes.
work out how to do that. Another question from roughly how much does a test cost? So it really depends what you're testing, I suppose, doesn't it?
Yes, I mean, I would have to. I'm sorry, I would have to refer you to the site, but it's.
Yes.
I think it's about £200, if I'm not mistaken. But OxfordAuthentication.com is gives you the current pricing, because there are some differences.
Yeah. And what tests are actually being done, and of course, I suppose the collectors have to put that in the context, don't they, of just what the value they hope it will add to their object.
Yes, because the customers of authenticity testing are museums, are private collectors, are auction houses. There's a whole range of people who are interested in the authenticity of ancient objects. So.
Yeah. Well, I think that's the end of the question. So, I mean, thank you, Greg, so much. That was a really informative talk. It was
thank you.
Yeah. I mean, just seeing such a complex topic broken down so that, we can be at least reassured if we're going off buying this these ceramics, that we have at least some clue that they're authentic, and how we get commercial applications from such a tiny physics effect, and how those electrons could just give up their secrets.
Yes.
And really seeing all those examples put together of all those very, very strange and wonderful and amazing objects, absolutely amazing. So, huge gratitude to you from everybody on the call, and thank you so much from the Hereford and Worcester branch as well. So
thank you for inviting me for this opportunity.
I really enjoyed it.
Thank you.
Okay, so I think we are all going to be cut off now. But thank you very much to everyone for joining us, and hope to see you again soon.